So what is a wave? Can anyone define a wave for me or describe a wave to me? So a propagation started by a disturbance. What is propagating? Something is moving, something is propagating. So you start a disturbance, you start movement, you start a vibration, you start, you stand up in a stadium and that motion propagates, right? That's a wave. When you stand up in a stadium and then your neighbor stands up and then the following neighbor, are you physically moving in the direction of the wave? No. How are you? What is your motion like when you're standing up? I mean, if you had to describe your motion, what would you say you're doing? You're standing up. Yeah, you're standing up. You're raising your hands maybe, and then you're sitting down. Right? You have gone up and down. Which way has the wave moved? That way, right? Or that way, depending on who's looking at you. So it's moved perpendicular to the direction in which you moved. Right? So you are the medium. You have done something. You have done some moving. The wave has done something too. Your motion is related to the wave motion, but it's not in the same direction. Okay? And it's not as though the medium is moving along with the wave. That is to say, when I'm speaking now, the way the sound is getting to you is that the air in front of my mouth is vibrating, and that vibration is traveling to each one of you because the vibration is going outwards in all directions. But those air molecules that are in front right here are not traveling to you, right? They're just moving back and forth. And then the disturbance, as you said, which has been created, the energy that has been sent out from here, from my speaking, is traveling to you. So a wave is a disturbance that carries something. It carries some information, carries some energy. Okay? You may or may not need a medium, but you have that disturbance traveling through a medium. How is that wave generated? Through some kind of movement. Okay? So this is what we just discussed. The medium is moving, the wave is moving, but they're not moving in the same way. Okay? The medium is not physically traveling in the direction that the disturbance is traveling. Okay? Everybody kind of gets this? Now, what are the ways that the medium can move? Can we begin to describe this wave a little more carefully, a little more concretely? So what are the different types of waves that you can generate? Yes. Yes. So if I did this for you, if I showed you this picture, okay, what kind of wave would you call this? Anyone have any words to describe this? Yes. Transverse. What does transverse mean? Say that again. Okay, a wave that moves like that is a transverse wave. What is it about the way it's moving that makes it a transverse wave? Anyone? Yes. So the disturbance is in a vertical direction, but the movement of the wave is in the horizontal direction, right? So the motion of the medium is perpendicular to the motion of the wave. Okay? So at this point, let me actually stop lecturing and show you some examples of this. So I have over here a piece of equipment called a shive. And so what I was showing you on that little animation over there was something like this. So it's a disturbance that traveled back and forth. You saw something interesting happen to it at this end. Okay, we'll talk about that in greater detail in a little bit. But for now, it's traveled there and it's traveled back and it's continuing to do that. And then eventually it dies out. Why does it die out? Yes, so the energy that I've put into it by actually physically moving it is not all going into the actual motion of the wave. Some of it is being lost, as you said, to friction or other things. Okay? So, but if I didn't have those frictional losses, potentially this could keep going for a very long time or forever. So that is one. Now I'm going to ask you, what's the difference between that? So once again, let me show that to you. This and the following. So there is a difference? Well, of course, you notice that the difference is in one case I just did it once and stopped. And in the other I'm continuing to do this. So what is the difference between those two things? I tried to make the sizes of the bumps the same. So yes. So so you've pointed out a few different features of that wave. You've talked about the height of the bump. We'll come back to that in a second. You've also talked about the repetitions. You use the word frequency. Okay, so in one case, what I was doing is, I was doing this once and then stopping. In the other case, I was repeating it. When I'm repeating something, there is a pattern to that repetition. There is a frequency or a repetition time, if you like, a period of repetition. Okay, so so that's what, the first of these is what I would call a wave pulse, an impulse, if you like, an impulsive wave. And the second would be a periodic or wave or a periodic oscillation. So this is one kind of wave. Let me show you another kind of wave and ask you what's the difference between what I showed you there, and just hold this end gently. So, have all of you played with Slinkies when you were little? They're the most fun toy. Anyway, so if I take a Slinky stretched out like this, one thing I can do is, do you all see something moving? So what is that? And how is that different from this? There's some similarities, right? It also moved across, yeah? Yes, so the way the medium itself was moving is different in the two cases. In this case, the medium was moving perpendicular to the direction in which the wave was moving, as you pointed out then. And as you've just said, here the medium is moving in the direction of the wave. Okay? So if this is a transverse wave, transverse just means perpendicular. This is longitudinal, in the direction of the wave. Okay? You can also set up a vibration in this, but there's a lot of frictional losses and damping in this, so it's hard to maintain. You can also set up a transverse wave pulse in a Slinky. Oops. This is the problem with Slinkies, is that they're very delicate pieces of equipment. So I'll try not to. My amplitude was too large in that one. Okay. So you see, you can generate a transverse wave pulse and a longitudinal wave pulse in the Slinky. Okay, now you basically know everything there is to know about waves. Thanks. And all that remains to be done is to say all those words again to you. So the words that I said were that if I have just a single input of energy, a single disturbance that travels, and then it either keeps going or hits a boundary and bounces back, that's called an impulse. So the difference is this it's generated once and it travels. Here, what I'm vibrating is continuing to vibrate. And if you put your hand here, do you notice that if I just focus on the black thing, it's going up and down. It's not going forward at all. And yet, if I take that up and down motion of this and move it forward in time, this is basically showing you what it's doing in time. So if I take that up-down motion, and instead of putting it here, I say, okay, I'm going to represent how this looks in time. So as it's going up and down, I'm walking forward. What you get is something that looks like our normal representation of a wave. And our normal representation of a wave is usually a particular function. Anyone know what this function is? A sine or a cosine, if you like. Okay, that's how you represent waves. Okay, so that is an oscillation. So this, even a stadium wave, is something that's a transverse wave. The first slide was distinguishing between impulse and oscillation. This is distinguishing between transverse and longitudinal. Okay. So this, for example, could be a wave generated in air. Sound is an example of a longitudinal wave. So a stadium wave is a transverse wave. A water wave is a transverse wave. That wave that I generated on the Slinky was a longitudinal wave. Sound moving through air is a longitudinal wave. And as I said, it's not as though the air molecules are traveling from one end to the other. The air molecules are just going back and forth, and the disturbance travels from one to the other. So let's try out our clickers. Okay, so can anyone tell me why most of you chose one and why the others are maybe not the right answer? That's often more instructive to know.
It's the same example. Sit in your place, you get up, and the wave moves horizontally. So same thing with the ribbon. You sit up, you put it up, and then it moves horizontally.
So the ribbon will move up and down, and what will travel down from left to right? Not the ribbon, right? It's stuck in one place of the rope. So the ribbon is just moving up and down. But what is it that's moving from left to right? The energy or the disturbance or the wave itself. So the ribbon will once again move when the wave comes back, if it does come back. It will indeed move. So 3 is not right because the ribbon is going to move up and down as the wave moves through. And it would move forward and backward if I had tied it to the Slinky, for example, and I were generating a longitudinal wave. But the question says in particular that it's a transverse wave pulse, so I've hidden that with this. So the question says transverse wave pulse, which means it's going to move up and down if the wave is moving left to right. And I hope it doesn't fall off the rope and I've tied it on correctly. Oh, that is because I moved things down. So that's not right. I moved the underlining got misplaced. formally, what are the physical quantities you need in order to represent the wave? In order to fully describe a wave, there are a few things you need. Now we are talking not about an impulsive wave, but something that's repeating, a repeated oscillation. Then you could say, if I'm representing the motion of a fixed point as a function of time, so going back to this. So now imagine I'm representing this particular animation over here. So this point, this black point is going up and down. So if I want to represent that, oops. All right, I'm going to draw that sine wave in time. What this is saying is, remember, all graphs, all physical representations of what's actually happening to something, how something is moving, they're telling a story. And the story this is saying is, when I started my stopwatch, so this is time, remember, at time t equals 0, that's when I start measuring, it's at a certain position. At a later time, this is the position it was at a later time there. So this is telling you what the position is at any given time. Okay? So the amplitude is the furthest it moves from its undisturbed position. Okay, so if I'm sitting and I stand up and I stretch my arms out, the amplitude will be where my arm began and where it ended. All right. So if I take any given point on the object and see how far that point moves from where it was when it was undisturbed, that's the amplitude. It's the furthest displacement, because you see the displacement from equilibrium, the black line here is the undisturbed position. The position can be anywhere in between the amplitude in one direction and the same amplitude in the other direction. So when something is moving, here is the undisturbed position, and it goes both above and below that undisturbed position. So when I talk about the amplitude, it's the furthest distance it moves from the equilibrium position in one direction. Okay? And then it comes back to the equilibrium position, and then it moves in the other direction. What do I need to fully describe this wave? So one thing I certainly need is the amplitude. The second thing you need to know is how long it takes to get back to the place it began. So I can start observing at any time. Let's say I say at time t equals 0, it was here. I find the time it takes to come back to that position. I can start anywhere though. I can start here and say, let's find the time it takes to come back to this position. So what I call the period is a time between two equivalent positions when it's at a given point in space, okay, away from its undisturbed. So the same time period is between this point and this point, okay, or between this point and this point. It's the time elapsed in one full cycle of the motion. Okay? And once I know what happens in one cycle, I know what happens forever, as long as it continues. Yes. Yeah. So, I have this measure. It doesn't quite work. Okay, let's say this is my, maybe it does. Let's say this is my measure of a period, right? I can move this anywhere and say, I'm finding the time between two equivalent points on the wave. So it could be, okay, I'm going to put this down and wave my hands a little bit. It's between here, I've shown it between that crest and that crest. But it could be between this trough and this trough. It could be between this point and this point. Why? Because this is when it goes through 0. And you could say, well, it's going through 0 again over here, right? But when it was going through 0 here, it's going in the other direction. I want it when it's going through 0 in the negative direction. So I come back and I find it's going through 0 in the negative direction here. So you see, there's a lot of information in there. It's not just the position, there's also the velocity information there. There's also acceleration information in there. Everything is there in this one representation. Does that make sense? Any? Okay, so once I tell you the time period, I could also tell you how many of those cycles I can fit into a particular time period. So let's say my measurement unit for time is seconds. Then I can ask you, okay, if I know how long one cycle takes, can you then tell me how many cycles I have every second? For example, if I told you it takes half a second for one cycle, then how many seconds am I going to have? How many cycles am I going to have every second? 2. Let's say I told you it takes 3 seconds for every cycle. How many cycles am I going to have per second? A third. So how are you getting those numbers? You're just inverting them, right? So the period and the frequency are related. The period is exactly 1 over the frequency. So really, to specify this wave, I tell you the period and I tell you the frequency. Okay, very good question. Amplitude, when I say amplitude, I usually mean a positive number. And that's just telling you the distance it goes in one direction. So if I were talking about the position though, I would say the position is positive in this direction and negative in this direction. Okay, so the amplitude is the largest change in position in one direction. And the amplitude is a positive number. So y, which is the vertical position, y can be positive or negative. Okay, so this is fine. This is telling you how something that's moving up and down is moving in time. But then you might ask, this example that I showed you, I'm moving this up and down in time, so this is all very well for representing what this point is doing in time, but it's not really showing me what the wave is doing on the whole shive over here. It's also moving forward in space. So maybe there is a little more to this story. So you could represent a wave in space. That is to say, let's say I'm moving this and I take a photograph of this, snapshot. I freeze it at one instant in time. Okay? Then I'm also going to see something like this. I'm going to see something that looks identical to the previous graph I showed you. However, the x-axis now is position. Okay? So it's telling you, all right, so remember I'm using 2 position variables now. Y is telling me how far it's moving in the vertical direction. X, if I don't knock this thing up, X is telling me its horizontal position. Okay? So I've set up the wave and then I've taken a snapshot of it so everything is frozen in the vertical and the horizontal direction. And it looks like this. So this is telling you different points on the shive where they are at that particular instant in time. And then you notice that there is a repetition here too. There is a part of it that's up, there's a part of it that's down. Because as the wave is moving through this previous representation, as it's moving through in time, different points are moving up and down at different instants in time. So in the snapshot, different points in the medium are at different positions. Okay, so what this has told me is that at this point, this is how far that wave has moved in one cycle. Okay. So if on the previous graph I measured how long it takes to complete a full cycle, the period, and on this I see how far it's moved in one cycle, what is the information I've found? I've measured the time for one cycle. I've measured the distance it's moved in one cycle. What do those two give me? Yes, I heard the word. Who said that? Velocity. It tells you the wave speed. So it tells you how far I've traveled in that time. Okay, so one cycle over here tells you the distance moved, okay, between when the wave, this went up, this went down, in one time period, this is how far the wave has moved. So this tells me that I can get, and I'll write this and I'll stop, I'll get wave speed is distance over time period.